Welcome to this session. In the last class, we have seen that we have derived a standard eigenvalue problem in its general form, and we have seen that this will form a self-adjoint operator, and we have looked into the various properties of self-adjoint operator. Now we have appropriate background of going for a complete solution of a by using separation of variable. The first problem that we will be talking about a parabolic partial differential equation in 2 dimension. So, we will be working with a 2-dimensional problem. Parabolic partial differential equation. We will be defining 3 problems: first kind, second kind, and third kind. So, that will be depending entirely on its type of boundary condition we are dealing with. Del square u del x square, del u del t is equal to del square u del x square, and problem of first kind is with the boundary condition at t is equal to 0, and we will be talking about a well posed problem, parabolic partial differential equation and well posed. Okay, at t is equal to 0, u is equal to 0, at x is equal to 0, and u is equal to u naught, let us say at t equal to 0. So, well posed problem means non homogeneous initial condition, and x equal to 0 and x equal to 1, we have the differential boundary condition u is equal to 0. Now, what is the second kind? Second kind is at t is equal to 0, u is equal to u naught, at x equal to 0, we have du del u del x is equal to 0, at x is equal to 1, we have u is equal to 0. So, in this particular problem, we have the Neumann boundary condition at x is equal to 0, and third kind will be at t is equal to 0, u is equal to u naught, at x is equal to 0, u is equal to 0, at x is equal to 1, del u del x plus beta u is equal to 0. So, this will be the third kind of boundary condition. Now, let us solve one by one and see how the solution differs, and one can go about a complete solution of using separation of variable. So, let us solve for the first kind, parabolic PDE and well posed. So, let us look into the complete solution of that. So, del u del t will be is equal to del square u del x square, and at t is equal to 0, u is equal to u naught, at x is equal to 0 and 1, u is equal to 0. Okay. So, if this is the case, then we assume that u is a complete function of it is a product of 2 functions. One is it will be a sole function of x, another is it's a complete function of time. So, u is equal to t into x. Now, in the governing equation we are going to put this. If we put this in the governing equation, what we will be getting is x dt dt is equal to t d square x dx square. If you divide by x t, this becomes 1 over t dt dt is equal to 1 over x d square x dx square. Okay. So, now the left hand side is a function of time only, the right hand side is a function of space only, they are equal. So, therefore, they will be equal to some constant, and again this constant can be positive, can be negative, can be 0. So, so this has to be minus alpha square, and we have seen earlier that if this constant, so this constant can be, it is a constant, and constant can be 0, can be positive, can be negative. Okay. So, if this is 0 and positive, we will be getting a trivial solution, that we have already seen earlier. So, the constant has to be a negative constant. So, this will be equal to minus alpha square. Now, let us look into the spatial varying part. So, d square x dx square plus alpha square x should be equal to 0, subject to boundary conditions. So, this equation now, this is an ordinary differential equation requiring two boundary conditions to be solved, and two boundary condition of x will be on x will be basically the boundary conditions of the original problem will be satisfying the same boundary condition of the sub problem x. So, the boundary condition of this problem x will be having the same boundary conditions on the original problem on u. That means, at x is equal to 0 and at x is equal to 1, u is capital X is equal to 0. So, we have already seen the solution of this problem in the last class. The solution is, this is a standard eigenvalue problem with a special form. If you remember that a0 is equal to 1 in this case, a1 equal to 0, a2 equal to 0, lambda is basically alpha square, and a3 equal to the weight function is equal to 1. So, therefore, we have already looked into the solution of this. The eigenvalues will be n pi and eigenfunctions will be the sine functions. So, I am not going into the solution because we have already solved in the class. So, alpha n is equal to n pi, where n is equal to 1, 2, 3 up to infinity. There are infinite number of eigenvalues. The theorem we have already seen. The corresponding solution will be x n is equal to c1 sine n pi x. And let us look into the subscript n corresponds to the eigenfunction corresponding to nth eigenvalue. What is the nth eigenvalue? N pi. So, this is the nth eigenvalue. So, now let us look into the time varying part. If you look into the time varying part, 1 over t dt dt is equal to minus lambda n square minus alpha n square. So, it is n square pi square. So, t will be c2 exponential minus n square pi square t. Now, we can get a complete solution. So, this t we should have a subscript n, because it will be corresponding to nth eigenvalue. So, therefore, the complete solution will be, so what is un corresponding to nth eigenvalue is Tn xn, and C1 and C2 will be multiplied, and it will be giving a new constant Cn exponential minus n square pi square t sine n pi x. So, what will be complete solution? U will be superposing all these independent eigenvalues, independent solutions. So, we will be adding up all the solutions corresponding to each eigenvalues and eigenfunction, and we will be formulating the complete solution. So, n is equal to 1 to infinity. So, therefore, this will be nothing but n is equal to 1 to infinity Cn exponential minus n square pi square t sine n pi x. Okay. So, that gives the complete solution of x and t, only the constant Cn has to be evaluated. Now, if you look into this problem, we had three, we have this equation was del u del t is equal to del square u del x square. It is order 2 with respect to x, order 1 with respect to t. We had an initial condition at t equal to 0 and two boundary conditions at x equal to 0. We have already used up these two boundary conditions while formulating the solution of x varying part. So, now only one condition is left behind, that is at t equal to 0, that is the initial condition, and we have only one constant that has to be evaluated. So, using the initial condition at t equal to 0, we will be evaluating this constant Cn. At t is equal to 0, we have u is equal to u naught. So, just put this condition in this equation and see what we get. So, u0 is equal to summation of n equal to 1 to infinity Cn sine n pi x. And we have already proved in the last class that the eigenfunctions will be forming the orthogonal functions. They will be the orthogonal functions with respect to weight function 1 in this particular case. So, what I will do next? I will be multiply both sides of the equation by sine m pi x dx and integrate over the domain of x from 0 to 1. So, multiply both sides by sin m pi x dx and integrate across domain of x 0 to 1. So, if you do that, usually is constant, this will be sin m pi x dx is equal to 0 to 1 summation C n sin n pi x sin m pi x dx. So, now if you open up this summation on the right hand side, now all the terms will vanish because of the orthogonal property of the sine function, but leaving behind only one term when m is equal to n. We have already seen that orthogonal, the eigenfunctions are orthogonal to each other for two distinct eigenvalues m not is equal to n. So, when m is not equal to n, then integral sin m pi x sin n pi x dx will be equal to 0 to satisfy the orthogonal property of the eigenfunctions that we have already proved earlier. So, only one term will survive in this infinite series on the right hand side, that will be m is equal to n. So, C n integral 0 to 1 sin square n pi x sin n pi x, and when m is equal to n. So, sin n pi x sin square n pi x dx. And now, we change the running variable m into n. So, what we will be getting is C n is equal to u 0 integral sin n pi x dx from 0 to 1 integral 0 to 1 sin square n pi x dx. And if you it's very trivial to show that this value is half. So, this will be always half. So, it will be having 2 u naught and sin n pi x. So, minus cosine n pi x divided by n pi, then you put the values 0 to 1. So, these will be 2 u naught cosine n pi minus cos 0 is 1. So, it becomes 1 minus cosine n pi divided by n pi. So, that is the value of C n. So, now we will be getting the complete solution. If you write the complete solution, u as a function of x and t will be nothing but summation n is equal to 1 to infinity 2 u 0 1 minus cosine n pi over n pi exponential minus n square pi square t sin n pi x. 2 u naught can be taken out of the summation sign, because that will be basically a constant. So, this gives the complete solution of the parabolic 2-dimensional parabolic partial differential equation of the first kind. Now, let us look into the solution of parabolic well post parabolic partial differential equation in second kind. Solution for second kind problem. So, we have del u del t is equal to del square u del x square, where t is equal to 0, we have u is equal to u naught, at x is equal to 0, we have del u del x is equal to 0, and at x is equal to 1, we have u is equal to 0. So, again we will be looking for a separation of variable type of solution. We assume that the solution is composed of multiplication of two terms. One is purely a function of x, another is purely a function of time. If you do that, then this becomes 1 over t. After separating the variables, it becomes 1 by t dt dt is equal to 1 over x d square x dx square. Again, this will be for entirely, the left hand side is entirely a function of time, the right hand side is entirely function of space. They are equal, they will be equal to some constant, and that constant can be 0, can be positive, can be negative. We have seen earlier that if it is 0 or negative, if it is 0 and negative, then we will be getting a trivial solution. So, if it is 0 and positive on the right hand side, then it will be giving a trivial solution. So, this constant has to be a negative constant. So, this has to be equal to minus alpha square. So, if that is the case, we can formulate the standard eigenvalue problem in the x direction. So, that will be alpha square d square x dx square plus alpha square x equal to 0, and this spatial varying part will be satisfying the boundary conditions of the original problem in the direction of space. So, therefore, at x is equal to 0, we will be having dx is equal to 0, and at x is equal to 1, we have capital X is equal to 0. In fact, we have already solved this standard eigenvalue problem earlier, and if you remember, the eigenvalues were 2n minus 1 pi by 2, and the eigen functions will be the cosine functions. So, let us write that the eigenvalues lambda alpha n are 2n minus 1 pi by 2, and eigen functions are cosine functions, cosine, let us say alpha n x. Okay. So, the corresponding to the time varying part. So, we will see dt 1 over t is equal to minus alpha n square. So, it will be T n will be nothing but C2 exponential minus alpha n square t. So, we can get the complete solution u of n is equal to nothing but T n x n, and C2 and C1 will be multiplied, giving to a new constant C n exponential minus alpha n square t cosine alpha n x. Okay. And we will be getting the complete solution by superposing all the solutions n is equal to 1 to infinity as C n exponential minus alpha n square t cosine alpha n x. Now, we have already seen we have already used up the two boundary conditions in the spatial direction. Now, what is left is this constant has to be evaluated. We will be evaluating this constant by utilizing the boundary condition at t equal to 0, which is nothing but the initial condition. U is equal to 0 is equal to u naught is summation n is equal to 1 to infinity C n cosine alpha n x. We will be evaluating C n by utilizing the orthogonal property of the eigenfunctions as we have done earlier. So, what we will be doing? We will be multiply both sides by cosine alpha m x dx and integrate over 0 to 1 on both sides, and then only one term will survive in the right hand side if you open up the summation series, because all the other terms will be equal to 0 in order to satisfy the orthogonal property of the eigenfunctions for corresponding to different eigenvalues lambda n and alpha n and alpha n. So, therefore, we will be having only one term on the right hand side after opening up the summation series, that will be the one which will be equal to when lambda alpha n is equal to alpha m. M is equal to n, only that will be survived. So, using the orthogonal property of the eigenfunctions, we can evaluate C n as u0 integral cosine alpha n x dx 0 to 1 integral 0 to 1 cos square alpha n x dx, and if we can really do this, this will be again turning up to be half. So, this becomes 2 u naught, this will be sine alpha n x divided by alpha n from 0 to 1. So, sin 0 is 0. So, only one term will survive here, 2 u 0 sin alpha n divided by alpha n, where alpha n is equal to 2n minus 1 pi by 2 the eigenvalues, and the index n runs from 1 to up to infinity, because there are infinite number of eigenvalues present in this system. So, if you write down the complete solution, u x t will be nothing but 2 u naught summation n is equal to 1 to infinity sin alpha n divided by alpha n exponential minus alpha n square t cosine alpha n x. So, this will be the complete solution, and alpha n is equal to 2n minus 1 pi by 2. So, this is the second kind of well posed parabolic problem. Now, let us look into the third kind of problem. So, it will be the similar type of equation. So, governing equation remains the same, del u del t is equal to del square u del x square. This is a third kind well posed problem, and at t is equal to 0, u is equal to u naught. At x is equal to 0, we have u is equal to 0, and at x is equal to 1, we have del u del x plus beta u is equal to 0. So, it is a Robin mixed boundary condition prevailing at the boundary at x equal to 1. So, now we will be doing again separation of variable type of solution. So, u is equal to x of x multiplied by t of t. After putting these in the governing equation and by separating of variables, one will be having 1 over t dt by dt is equal to 1 over x d square x dx square. And again this will be equal to minus alpha square, and we will be having the eigenvalue problem in the spatial direction, in the x direction, as d square dx square plus alpha square x is equal to 0, and the boundary condition of the spatial varying part will be satisfying the boundary condition of the original problem. So, at x is equal to 0, we have u is equal to 0, capital X equal to 0, and at x is equal to 1, we have dx plus beta x is equal to 0. Again, this standard eigenvalue problem in the simplified version, we have already seen the solution earlier. The eigenvalues of these problems are coming from the solution of the roots of the transcendental equation, alpha plus beta tan alpha equal to 0. So, eigenvalues will be roots of alpha n plus beta tan alpha n is equal to 0, and eigenfunctions are the sine functions. Okay. So, we have already seen that the roots of these transcendental equations will be the eigenvalues. There are infinite number of roots present of this equation. So, therefore, there are infinite number of solutions are also present for this system, and each solution is the eigenfunction, and nth solution corresponding to nth eigenvalue is the nth eigenfunction. Now, the time varying part, as we have seen earlier, that remains the same. Time varying part will be Tn C2 exponential minus lambda n square t, and we can get the complete solution as u is equal to summation of un is equal to summation of Cn exponential minus lambda n square t sin minus alpha n. This will be alpha n. Okay, this will not be lambda, will be alpha n square t sin alpha n x. So, u, let us write in a clean neat form, Cn exponential minus alpha n square t sin alpha n x. And again this equation can be this Cn will be evaluated at the boundary condition, the initial condition at t equal to 0. At t is equal to 0, we had u is equal to u naught. So, therefore, u naught is equal to summation of Cn sin alpha n x, and again Cn can be evaluated by exploiting the orthogonal property of the eigenfunctions sin alpha n x. That means, we will be multiplying both sides by sin alpha m x dx and integrate over the domain of x from 0 to 1. All the terms on the right hand side will be vanishing except the term when m is equal to n when we open up the summation series. So, let us get that. So, Cn will be u0 integral sine alpha n x dx divided by integral sine square alpha n x dx. So, let us look into the solution. So, sine square integral sine square alpha n. So, first let us look into the solution of 0 to 1 sine square. I am talking about the denominator, sine square alpha n x dx. So, this becomes just multiplied by half. So, this becomes 0 to 1 2 sine square alpha n x dx, and utilizing the function sine 2x. What is sine 2x? Sine 2x is equal to okay. So, let us look into how this can be evaluated. Sine square alpha n x dx from 0 to 1 is equal to half 0 to 1 2 sine square alpha n x dx. So, cos 2 n x 2 alpha n x will be nothing but cos square alpha n x minus sine square alpha n x, and this becomes 1 minus sine square. So, this becomes 1 minus 2 sine square alpha n x. So, therefore, 2 sine square alpha n x will be nothing but 1 plus cos 2 alpha n x. So, let us substitute here. So, 0 to 1 sine square. So, it is a denominator only, alpha n x dx will be nothing but half 0 to 1 1 plus cosine 2 alpha n x dx. So, let us carry out the integration. Half, this will be 1 plus integral of cosine 2 alpha n x dx is nothing but 1 by half 1 plus this will be sine 2 alpha n x divided by 2 alpha n. Okay. We express sine 2 alpha n in the form of tan. So, 0 to 1 sine square alpha n x dx now becomes half 1 plus divided by 2 alpha n. Sine 2 alpha n is nothing but 2 tan alpha n divided by 1 plus tan square alpha n, and we have seen that the eigenvalues will satisfy the governing equation as alpha n plus beta tan alpha n is equal to 0. So, therefore, tan alpha n can be written as minus alpha n divided by beta. So, if you substitute there, so this denominator now becomes sine square alpha n x dx is equal to half 1 plus 2 alpha n. 2 tan alpha n will be multiplied by 2, tan alpha n will be minus alpha n by beta, and this will be 1 plus alpha n square by beta square. So, 2 will be cancelling out. So, this will be half 1 minus this alpha n will also be cancelling out. So, it will be 1 minus alpha n alpha n will be cancelling out. So, it will be 1 by beta plus alpha n square by beta. So, this will be half there is a sign here. So, 2 sine square alpha n x will be it will be coming on the other side. This will be minus. So, this will be minus. So, this will be minus. this will be minus. So, again we will be having this will be minus, there will be minus sign here, minus minus will be plus. So, it will be plus half 1 plus 1 beta square plus alpha n square divided by beta. So, you will be getting half beta square plus alpha n square is equal to beta square plus beta plus alpha n square. Okay. So, let us look into the complete solution now. So, this is the denominator we will be getting. Let us look into the numerator. The numerator of the solution is 0 to 1 sin alpha n x dx. So, this will be minus cosine alpha n x divided by alpha n from 0 to 1. So, it will be alpha n 1 minus cos n pi. Okay. So, now we will be getting the complete solution of C n. C n is equal to u naught. So, numerator is 1 minus cosine n pi by n pi, and denominator is there will be multiplied by, it will be reverse. So, it will be 2 beta square plus alpha n square divided by beta square plus beta plus alpha n square. So, we will be having 2 u naught 1 minus cosine n pi divided by n pi multiplied by beta square plus alpha n square divided by beta square plus beta plus alpha n square, and we will be having a complete solution. U as a function of x and t is summation of it will be 2 u naught summation of 1 minus cosine n pi divided by n pi beta square plus alpha n square divided by beta square plus beta plus alpha n square sin alpha n x. So, this will be the complete solution for the third kind of parabolic partial differential equation, a well posed problem with the boundary condition as a Robin mixed boundary condition. Now, alpha n will be evaluated from the roots of the transcendental equation that we have already talked earlier. Alpha n plus beta tan alpha n equal to 0, alpha n plus beta tan alpha n equal to 0, alpha n are the roots of this equation. Beta is a known parameter to us, so that will be there. So, this will be giving a complete solution of u as a function of x and t. So, we have seen the how to solve by using a separation of variable type of method a parabolic partial differential equation of second order, which is a well posed problem. In the next class, what we will be doing will be solving a second dimensional second 2-dimensional problem only, which will be, but it will be an actual problem. It is not a well posed problem. It is actually a practical problem. How this problem will be non-dimensionalized, and then it will be giving an ill posed problem. Then we will be converting the ill posed problem into well posed problem. Then we will be solving it. Thank you very much.